Hello, everyone. Thank you for this great opportunity for us to present our research paper titled Explainable Computer Vision Techniques and Deep Transfer Learning for Tomato Disease Diagnosis. This is Via Drake on behalf of the whole author team from Makerere University, Department of Computer Science. Tomatoes are one of the most popular vegetables grown in Uganda due to their high demand, both locally and for export. This has led to many farmers being involved in the growth of these tomatoes. However, these farmers are currently facing a challenge of leaf disease diagnosis outbreak, like facing tomato leaf diseases like bacterial spot, tomato curry virus, and late blight, among others. So these diseases have led to significant losses affecting the quality and quantity of their tomatoes, hence like decreasing on their demand or like on the market in the outside. So early and proper preventive measures need to be considered for these farmers to continue gaining into the tomato growth business. So farmers mostly relied on their own visual inspections or advice from agriculture experts and experienced farmers for this disease detection. To some point, the method helps, but it is expensive, time-consuming, and not always accurate, because some diseases have the same symptoms. So it's hard to really differentiate between like early blight and late blight, bacterial spot, and curry disease. So luckily enough, recent advances in artificial intelligence and deep learning have offered great potential for early disease detection. Many deep learning models have been implemented, indicating outstanding results across different image classification tasks, such as plant disease recognition. So David P. and Shadara P. used a deep learning model with AlexNet and GoogleNet architectures that achieved good plant disease classifications. Then Smith Johnson also employed a transfer learning with ResNet 50 architecture, enhancing its capability for tomato disease detection and achieving an impressive accuracy of 92%. Then also Sagara used explainable artificial intelligence methods to verify the model's prediction. So in this study, although different deep neural networks have been implemented and are used, there's a challenge that they need a large, extensive annotated dataset to ensure higher generalizability and transferability. But such datasets are scarce due to their high cost annotation process. And the use of these small datasets lead to challenges like inadequate feature extraction, overfitting, and sampling biases. Furthermore, many deep learning models require powerful hardware since they are computationally intensive, like the vision transformers and CNN models. Hence, it's hard to deploy them on small gadgets like smartphones or low-cost computers. And these are the type of gadgets that these farmers really use. Additionally, these deep learning models are black boxed in nature. So farmers don't know like which features or how these models came to their predictions. So their explanations for their inferences are not transparent. So farmers need more transparent models that they can trust. So in this model, we want to use transfer learning to improve the performance of deep neural networks on small data sets, then integrate explainability into the developed pre-trained models, then evaluate the performance of different pre-trained models, and employ explainability techniques, and also demonstrate the practical applications and benefits of the proposed approach in improving tomato disease diagnosis. So in our contribution, we have implemented and evaluated deep transfer learning models for tomato disease diagnosis, then made explanations using LRP, GradCam, and SHARP to show the relief regions responsible for the different predictions. Then compare the effectiveness of the different explainable techniques used. So to do this, there are different steps we've gone through. That is starting with data collection, then carrying out exploratory data analysis on the data collected. Then from that, we did data pre-processing, that is preparing the data for training. We split the data set into training, testing, and validation data sets, and used the data set for future extraction, model training, model testing, and then model evaluation using different evaluation metrics like F1 score, precision, recall. Then we did model comparison of the different transfer learning models that we've used, then applied explainable implementation to solve the black box nature of these models, then compare the different explainable artificial intelligence on different models. For the data set, we got leaf images from the plant village data set containing 54,303 leaf images from 38 different plants, but our concentration was on the tomato leaf images. So we got 10,000 train images of different classes. That is 9 classes of affected leaves, and then 1 class of healthy tomato leaves, as you can see. So after collecting our data set and knowing which number is there, we did exploratory data analysis. Under exploratory data analysis, the main techniques we used were edge detection and contour detection. For edge detection, you have to visualize and understand the structure of different features of leaf images, since each disease affects the structure in a different way. Then we used Canny algorithm to find the boundaries or edges of the images, determining where the variation in shape and texture was, because this is an important feature in differentiating between like different leaf diseases and between healthy and unhealthy leaf. Then under contour detection, I had to visualize the outlines of affected areas and veins of leaf images, which are important feature for prediction. So through the whole process of explored analysis, we provided variable insights into the data set, guiding the pre-processing and modeling decisions for the tomato leaf disease classification task. So under pre-processing, we did different techniques. That is, we started with data augmentation using techniques like resizing the images, rotating the images, flipping the images to increase on the number of images, because to solve the problem of the small data set and then solve all the challenges caused by the small data set challenge. Then we had to resize or rescale the images to a 224 by 204 size, which is the input size for most of the models we are to use. Then creating or downloading the base model. This can be ResNet, VGG16, or the models we used. Then freezing the configurational base of the downloaded model for future extraction. So under future extraction, extracted features like edges, texture, color. These are used in distinguishing between different leaf diseases and health diseases. Then we did batch normalization. So through this, new fully connected layers were added to the model and adopted specifically for tomato leaf disease that is under fine-tuning, allowing the weights of the top layers to be updated while the pre-trained features remain intact. These layers were trained on the tomato leaf dataset, allowing the model to learn the specific features that differentiate between the different classes. So the extracted features were passed through the newly added fully connected layers. Then we did hyperparameter tuning using Optuna. This was done to pick the most, like the higher performing parameters, like the learning rate, the batch size, the different dropout rates, so that we could optimize the training and get higher performance. So after hyperparameter tuning, we did more training to get like higher performances. So the classification head was added for prediction generation. Then we did the training. Different pre-trained models were used. So we used the EfficientNet B0 model. We used the RaceNet 50. We used the VGG16, VGG19, and Vision Transformer. The first four EfficientNet, RaceNet, VGG16, and 19 are CNN models. Then Vision Transformer is based on the transformer architecture. So these are the results we got. First, we trained before transfer learning. Those are the custom CNNs. And Vision Transformer is not a CNN model, and it performed better than all other models. Majorly, its high performance is due to its self-attention to capture global dependencies and relations. So the self-attention allows the model to understand the relationship between different parts of the image by assigning important scores and focusing on the most relevant patches. So it's a self-attention makes it more, like helps it to capture more global dependencies. Then we see that EfficientNet performed better than all other CNN models, and this is due to its compact and efficient architecture that balances the precision and recall. Then RaceNet performed better than the two VG16 and VG19 due to its residual connection that helps it mitigate the vanishing gradient, a challenge for deep neural networks like VGG16 and VGG19. Then after pre-training, that is, we are using a different weights, like already the knowledge learned from the pre-trained models, majorly trained on ImageNet dataset, to be used into like retraining, saving the time and the computational resources. VGG Vision Transformer still performed better than other models, having a 97.91 performance, like F1 score, then 98.50 accuracy. EfficientNet was still the second, followed by RaceNet and VGG performing poorest. So Vision Transformers are like use less memory, less computational resources, lightweight and fast. Hence, can be used on small gadgets as compared to other models, and then performed better than other models on the small data set that we had, making it the best model and the model that we can implement and use on the small gadgets like smartphones. Then this is a graphical representation of training and validation metrics for specifically RaceNet tomato leaf disease, showing how like accuracy and loss were changing over an increase in the number of epochs. Like shows the accuracy was going up as the loss was going down. Then from that, to solve the problem of like black box nature of these pre-trained models, we used 3 different explainability techniques. Use gradient weighted class activation mapping. We used sharply additive explanations and layer-wise relevance backward propagation. GradCam uses gradient target features into the final convolutional layers, generating highlighting the regions considered in the model's prediction, as we can see. Then LLP, for it assigns relevance scores to each feature. So it works by propagating the output feature backward through the model network layers, calculating the relevance from output to input neurons, showing the most relevant features visualized into a feature map. So we use GradCam on EfficientNet because GradCam is mainly for CNN models, and then we used LLP on vision transformers. We also use Sharp, that is, it assigns each feature of the output a Sharp value. This is based from the game theory. So a positive value indicates like the positive feature is considered, and the negative value indicates the negative features that were considered. So this shows that, okay, Sharp can show us the features considered into generating the prediction. So in conclusion, we've demonstrated the effectiveness of transfer learning in tomato leaf disease detection using pre-trained models like Vision Transformer, EfficientNet, VG16, VG19, and ResNet models on a small data set. Then we have employed explainability techniques, uncovering hidden insights into the pre-trained model's prediction, thereby fostering transparent tomato leaf disease. So in this, we can help Ugandan farmers into their early prediction of these tomato diseases while providing like transparency into these models so that they can trust the whole process. So the limitations is that some expandable techniques cannot be applied on all the models, and then data limitations. Now recommend the creation of a tomato leaf disease dataset based on Ugandan tomatoes or Ugandan condition, then exploring more scalable techniques in age detection, because only the age detection can be used into classification of these tomato leaf diseases. Yes, thank you so much.